Welcome back again to Alpha Found. Estimating the values of the low ideal beta and high ideal beta has proven to be a challenge. A rigorous solution is not available. One possible way to solve the problem of ideal beta estimates is to use the zero-intercept model for the low and high CAPM beta portfolios. Here is the reasoning. In CAPM, all of the idiosyncratic risk sums to zero for the aggregate of all securities in each time period and for each security individually across time. In the perturbation risk model, this is not the case. However, the average perturbation for a well-diversified portfolio over a long period of time should average out to be close to zero, since the expectation is zero and the process is mean reverting. This is just the assumptions of equation 12.4 as they were applied to 12.5a and b. It is unlikely for an individual stock or an under-diversified portfolio to meet this standard. These videos are about model building, not data analysis. However, in the real world, it is easy to find examples where the zero-intercept model gives an answer that is outside the range given by the estimation methods shown in the last video. There are two possibilities. One, a large and diversified portfolio over a long period of time can generate excess risk-adjusted returns consistently for no clear reason, and therefore the volatility effect remains a mystery to some degree. Or two, the covariance between the perturbations is not zero. Table 16.1 set out 9 scenarios and the corresponding conditions needed to meet certain risk and return expectations. The derivations of the 9 conditions frequently use the phrase, assuming the covariance between perturbations is zero. Removing that assumption means the covariance between perturbations is not zero. Table 16.1 will be called the naive model. Putting the covariance between the perturbations back into the conditions gives us Table 21.1. Table 21.1 will be called the full model. Table 21.1. Expected relationship between OLS alphas and Sharpe ratios for different perturbation risk relationships, with the covariance between the perturbations not equal to zero. The perturbation risk ratio has a fluid definition in the full model. Conditions 1, 2, and 3 have this definition for the perturbation risk ratio. Conditions 4 and 5 have a different definition. Condition 6 has the same definition as in the naive model in Table 16.1. Finally, conditions 7, 8, and 9 have this definition. The derivations of the conditions in Table 21.1 result in some apparent inconsistencies. For instance, the derivation of condition 3 in Table 21.1 leads to the following. There is no longer one middle term but two. Either of the two middle terms is sufficient and neither contradicts the other. Also, the endpoint conditions are the important conditions and there is no difficulty with them. The form given for each condition in Table 21.1 seems best for the goals of these videos. Others may prefer a different form. It is important to notice something about the conditions of Table 21.1 that is not in Table 16.1. The high ideal beta corresponds with the high perturbation risk. The low ideal beta corresponds with the low perturbation risk. And the product of the ideal betas corresponds with the covariance between the perturbations equal to the correlation between the perturbations times the low perturbation risk times the high perturbation risk. The corresponding pieces do not have the same value, but they often have the same place in the structure of the conditions. For example, look at condition 7. The two left-hand terms have the same structure. Including the covariance between perturbations means all the previously derived formulas need to be rewritten and set to music. There are several hopeful avenues of approach available to solve the equations above. Unfortunately, they don't work. What is left are approximation methods. Full condition 9 is repeated here. Two substitutions into full condition 9 are helpful. Equations 21.10a and 21.10b can be rearranged to give the two substitutions have this result. In this mess of an inequality, all of the pieces are known except the covariance between the perturbations. To ensure that the denominator and ideal market variance of equation 21.18 are positive, two more conditions must hold. 1. The denominator must be greater than 0. And 2. The covariance between the high and low CAPM beta portfolios must be greater than the covariance between the perturbations. Condition 2 is necessarily true, but I will skip the proof. As a reminder, the covariance between the perturbations equals the correlation between the perturbations times the standard deviation of the low perturbations times the standard deviation of the high perturbations. To examine inequality 21.18, quarterly total return data for the components of the S&P 500 from the first quarter of 2015 through the fourth quarter of 2019 were used. Only those companies that were part of the S&P 500 for the entire period were included. Individual stocks were rebalanced to their initial weights each quarter. Without this procedure, the market statistics are not as clean as needed to make the assumptions work. Stated another way, the S&P 500 is really a different index from one quarter to the next unless sameness is imposed. It would be nice to compare to the same index in each time period, not a moving target. Let me squeeze in the disclaimer that this dataset, as constructed, suffers from survivorship bias and other problems. The following statistics were gathered while using the zero-intercept estimate for the low ideal beta and high ideal beta. I'm not going to read through them, but here they are for reference. Since the Sharpe ratio of the low CAPM beta portfolio is greater than the Sharpe ratio for the market, which is greater than the Sharpe ratio for the high CAPM beta portfolio, the full condition of Scenario 9 with the substitutions of equations 21.17a and 21.17b will be examined. Making a few calculations in the background, the denominator is greater than 0 when the covariance between the perturbations is greater than 0.0008807. And the covariance between the low and high CAPM beta portfolios is greater than the covariance between the perturbations when the covariance between the perturbations is less than 0.0022877. Therefore, the covariance between the perturbations is in this range. Once the covariance between the perturbations has been estimated, the variance of the low perturbations, the variance of the high perturbations, and the variance of the ideal market can be calculated from equations 21.17a, 21.17b, and 21.15. Making a table of potential values of the covariance between perturbations leads to another constraint. The lower part of the range for the covariance between perturbations leads to correlation above 1. Consequently, the range is constrained further such that the covariance between perturbations is between the numbers shown. Table 21.2 is the result. Estimated ex post covariance and variance of perturbations and full perturbation risk ratio for realized market data January 2015 through December 2019. The values of the statistics found in each row are all consistent with the market statistics from January 2015 through December 2019. Table 21.2 contains a strong relationship for the correlations between perturbations. This high correlation between the perturbations is the reason the market perturbations can be so large. If the perturbations were independent, it might be expected that the average across all securities would approach 0 in each time period. In the current state of model development, there is no quantitative reason to prefer one set of values over another in Table 21.2. Subjectively, a smaller value for the covariance between perturbations seems likely, but this requires the correlation between perturbations to be close to 1, which seems unlikely. The range of values in Table 21.2 for estimated quarterly ideal market and perturbation standard deviations are as follows. Curiously, the range for the standard deviation of the low perturbations is greater than the range for the high perturbations. Choosing a value for perturbation covariance in the middle of the range of Table 21.2 will attribute about 1/4 of the market variance to ideal market variance. The rest comes from perturbation risk. The time period chosen was one of low market volatility. This may provide insight into the problem of quantifying excess volatility. Stated differently, excess volatility by itself is logically the cause of most or all of the volatility effect because of its effect on OLS regression calculations. I'm going with most. Though only about 1/4 of the variance is coming from the ideal market risk, nonetheless, every entry in Table 21.2 leads to the correct values for the correlation statistics below. Lastly, though the correlation between perturbations is different in each entry still generates the same idiosyncratic risk. More details are in the next video.